Be our last lecture. And then next week's gonna be all office hours. During this time, I'll be here. So if you guys want to come hang out, do the homework, work on the practice final, you're welcome to. So next week I'll just be here. And I'll also be online as well. So if you want to have office or ask questions during office hours, just come online. I'm going to change my next week's office hours. So this is going to be next week's office hours, and I'll probably have two, I would say like 4 to 4:30 sessions online for people who are online and who work. So you can also ask me later in the evening. So yeah, well, we're gonna finish this pretty fast. I would say 10 minutes, 15 minutes, and we can all get out of here and go on vacation immediately. I'm trying to get out of here too. All right, so thank you for coming in today. So this is going to be the last thing we're going to talk about. So yesterday we just finished this example on Nyquist stability criterion. And basically, the takeaway is if you have encirclements about -1, that doesn't mean it's unstable. It just means that if you have right half plane poles, then the encirclements around -1 is okay. Um, when you see a lot of Nyquist plots and they say the system is unstable because it encircles -1, it's because there are no right half plane open loop poles. So like there are no open loop poles in the right half plane. And usually when we do design systems, we don't have open loop poles in the right half plane. But in this example, we do have open loop poles in the right half plane, but we do have a stable system as well with encirclements around -1. So the reason why I'm saying that is because in the next slide, we were talking about gain and phase margin, and the gain margin is just basically the distance from is the distance from this point to here. And by increasing or decreasing k, we actually reduce that point, that crossover point. So this k, adjusting k will change this size. Well, adjusting k changes this size. Or it's called this gain margin. And the phase margin is basically how much we have to rotate to have this crossover as well. And that's called the phase margin. And the phase margin will tell us how much lag our system can handle, and the gain margin will tell us how much gain we can change before we cross that -1. And so it's written on the chart, and it's kind of small, but the gain margin is going to be 20 log of A here. And then this phase margin is just alpha. So one thing we do know is when when the Nyquist plot passes -1, it becomes marginally stable. So that's going to be the gain and phase margin in relation to the Nyquist plot. I think it's a little bit more intuitive than reading the gain and phase margin on the Bode plot. And Nyquist plot mainly is just for checking stability when we do have time delays. Okay, so this next part is going to be, it's not in the textbook, but it's basically its relation to robust stability. On your updated slides, I do have a figure from the previous page, but I forgot to update my slides. So I'm going to just take a screenshot of this and move that out of the way. Oops. So this isn't in the textbook, and I'm not going to test you on this, but I just want to talk about its other useful property of using Nyquist stability. It's about robust stability, and we can actually use Nyquist plot to determine how much uncertainty our system ha can handle. One thing we're going to assume in this derivation is that we have no right half plane open loop poles. And even if we do, then we just need to interpret this a little bit different, a little differently. But we're going to assume an easier case. And basically, the way I model uncertainty, and this is a very simplified model of uncertainty. The way it's done in robust control is going to be a little bit more complicated, but I want to just remove the complications and just focus more on the analysis. So we're going to have this straight loop here, or this straight feed forward. And then we're going to have, so here's our control signal U. And then we have this uncertainty called delta. And it's an uncertainty that is dependent on, it's a function of frequency. So depending on what frequency we're at, the size of delta will change. Delta of S is our uncertainty. And it's a function of frequency. And then we now have our plant called G. Going out to our output Y. And this is going to be negative feedback. So there's different notations for this. I'm going to give you kind of standard notation, but I'm cutting out a lot of, or I'm simplifying this. But GP here is our actual plant, which handles uncertainty, which contains uncertainty. So here, if I were to make a block diagram GP is going to be equal to um, G times 1 plus delta, which is equal to G plus delta G. And basically, this is our uncertainty. Uh, One thing to know about this is when modeling is perfect, then delta of S is equal to 0 for all values of S. So then we just get our standard issue transfer function, which is G over 1 plus G. Yeah, but that's not the case though. So in reality, when there's uncertainty, then we actually get this transfer function form. It's going to be G times 1 plus delta divided by 1 plus G times 1 times delta. So if we were to look at this, we get this 1 plus G plus delta G. Are there any questions on this uncertainty block diagram I made, or it's everything I'm doing so far? This is just how we model uncertainty. We just add this little uncertainty block as part of the input goes through this uncertainty and we apply that signal to G. And then now we can quantify delta. Let's say we are off when we're using system identification and we build a model and then we compare it to our actual system, and it's off, we can then quantify that delta in terms of magnitude. Okay. So then basically when we're looking at the characteristic equation, because we characteristic equation, we're looking at the Nyquist plot of this. So we have 1 plus g plus delta g. And so what we're doing is we're taking the Nyquist plot of this. This is our Nyquist plot. And then we just shift the whole thing we don't shift it by 1. We just look at the encirclements around -1. That's why we have the 1 there. And then, so then this part here, this term here, like adds this uncertainty. It adds a radius. Okay, a radius around the plot. Radius. So what I mean by that is if we're looking at this Nyquist plot now on the left, I think there's too many letters on this thing, so I'm going to remove that. I'm gonna just draw it so it's a cleaner drawing. Okay. I'm going to have the same exact drawing, but there's without the text. And draw my unit circle. Make this a little bit bigger so I have more space to work with. So this is my unit circle. So that means -1 is right here. And then I'm gonna have my Nyquist plot in red here. And then basically what we're trying to do is here, I'm gonna label this. This is my Nyquist plot. Nyquist of G of S. This green radius here is actually going to be the length of G, evaluated to this as this frequency. And then I guess maybe hopefully you can just take this for granted. Shall do the same color, but this distance from here to there has the length of that magnitude of 1 plus G at that point. All right. And then finally, this delta G that I drew, I'll choose a different color. Creates this radius because we're adding on to this radius here now. And this here is delta G, this length here. It has a radius. So that's my uncertainty. And basically what we don't want is we don't want this bubble to grow so big that it crosses this -1 region, like kind of like that. If it does, then we're not guaranteed stability or robust. It might robust stability. Basically, what we're trying to do is we're trying to guarantee that this system will be stable with this amount of uncertainty. So I'm going to write down the conditions for robust stability. So basically, we want this circle to not encircle -1. This is why I'm talking about we're assuming no right half plane poles in the system, because if we have encirclement around -1, then this system is unstable. So that's going to be our condition. So then basically this indicates for stability. So for stability, we want 1 plus g, like this length here that I've defined, to be greater than the absolute value of um, delta times g, which is my uncertainty multiplied by g. And then we're just going to divide both sides by g. So we get this condition. So this is called robust stability. Is that our uncertainty needs to be less than the magnitude of 1 plus g divided by g. And this is for all s is equal to j omega. So this is at all frequencies. So if we meet this condition, we can guarantee that the system is going to be stable even with uncertainty. And this is where this derivation comes from the Nyquist plot when we were looking at robust stability. This is actually one of the main reasons why I brought this back into the curriculum, is because it's used in robust stability. And I think if that's a great class to take, because we always have modeling errors. So if you're ever asked to like model something and they say, well, how do you know this is going to work when you have modeling errors? You can do this sort of analysis and say that, well, our uncertainty is less than this condition that we defined down here. We're good. So that's why I brought this back. So even though this method was originally used to check for closed loop poles in the right half plane, which is something we can do very easily in MATLAB or Python or any computer, uh, we can still this other technique which came from it is used for checking stability when you have modeling error, which is a little bit harder to do on, well, I think it's still easy on computer, but you can now do it by hand. So that's it. We're done with all material. I'm not going to test this part on the exam. This is just a little bit bonus material that's not in the textbook that I think is very useful, because I honestly think Nyquist stability criterion by itself isn't that useful, but in relation to checking for stability with time delays using the phase margin and with robust stability, it is quite useful. So these are just the two takeaways. So Nyquist stability criterion helps us determine stability of our open loop systems without closing the loop. And we can use the Nyquist stability criterion to determine the gain and phase margins. And I actually forgot to add that we can also use it to determine how much uncertainty our system can handle under before it becomes unstable, or not if not when it becomes unstable, if it can become unstable. What we're guaranteeing here is that if we stay under this uncertainty, the system will always be stable. If the uncertainty exceeds it, it doesn't mean we will become unstable, because maybe that uncertainty only occurs at a certain frequency. All right, so that's it. Well, we're done with everything. I actually finished, I would say, 2 days earlier than I expected, 2 or 3 days earlier than I expected. So, I mean, I guess we're ahead of schedule. Next week, just office hours in class, like I said, and maybe I'll talk about classes on Monday as well, before like at the start of class, if you want to just tune in for that, and I'll be online as well. All right, thank you very much, y'all. One last thing is that I we will be getting surveys for this class, and I am going to be bugging everyone about it every day to take it. That's how I improve this class every year. So course evals. Yeah, yeah, it's anonymous. I cannot read it until December 21st, I believe, or something like that. So it's far after the final. And you also have to take it. You also cannot, like, you can only take it before the final. So if write a terrible final, that's not going to be considered. So no conflict of interest. But no, the evaluations genuinely do help me improve my class. So every year I read every comment and it's anonymous. So if you hated my class and you hate my guts, you can say that. I won't know who said that. If you liked my class and you said it was a great class, I won't know who said that either. So it really helps me improve content and make it better for the subsequent years. So yeah, I appreciate everyone and have a good Thanksgiving. And I will see y'all on Monday.